All right, welcome everybody to the first exam review for microcontrollers. So today I'm going to go over a few topics, starting with the need-to-know assembly instructions, then the registers and addressing modes, the memory map, and the stack. And that all should be on the test. None of those should be new material for you guys, right? All heard of those? Okay. So, now the the instructions can be found in the family guide for the MSP430. On page, well, actually, section 3.4.5, and that's around page 65. And you can print those out for the test. And I highly recommend you do so, and also print out a copy of one of the demo problems that he's given you, or the demo projects that you've used for your project so far. So, let's just go through some of the instructions. So in assembly, you have instructions, and each instruction either has a destination or a source and a destination. So there's either instructions like this, which have and a destination, like this instruction, where you add 1 to R15. Or there are instructions that have just 1, like this. Like the push instruction. And the push instruction is used to put stuff on the stack. But this only has 1 instruction, and that's a destination. So when you have a 2-operand instruction, like add, the result is always going to go in the second one, the destination. Okay. There's also another thing that you can do. The default for all the instructions is word operations, but some you can do a byte-wise operation. With a .b, so that you're only affecting a byte. Because in the MSP430 that we are using, the registers hold 16 bits, which are 2 bytes. So like say I have this register, and there are 16 values that it holds on to. So 16 bits, made up of 2 bytes of 8 bits each. And most of the, well, actually all of the registers are either going to be 16 bits, or word length registers, or 8 bits, byte length registers. All the general purpose registers, the ones that list from R4 down to R15, those are all registers that you can use to store variables and work with, and those are all 16 bits. But there are some registers that control specific parts of the MSP430, like the port 1 input register. And that actually holds only 8 bits corresponding to each of the pins in port 1. from port 1 pin 0 to port 1 pin 7. And on your launch pad, you can see each of those pins, and they're labeled, and you can see like the little trace on the wires on the launch pad going from the pins all the way to like the different buttons and LED lights. So, some important instructions to know, because that is all just like how they're structured and everything. But the ones that you need to pay particular attention to, or the ones that will be listed on previous tests, that's what I mean. And the capitalization for these doesn't matter, just be consistent. And this isn't an exclusive list of all the instructions. These are just the ones that commonly show up on his first test. So the add, the very first instruction, works exactly how you expect it to do. So you have two numbers. Say you have a literal value of and let's say you have a register. There's not really going to be any application where you add two literal numbers together. You almost always want to store the result in either the register or some other value, like a variable, or have the register index into an array. So let's say that at the beginning, R4 contains the hexadecimal value 001H. Oh, just a brief note, you can write hexadecimal values like this, or like this, but not like this. That's wrong. One or the other. Binary values are indicated like this, using the percent sign, and decimal values are regular. I'm pretty sure there's a way to represent octal values, but I've never used octal values in this class or even in Project Lab beyond this, so look those up. It's all in the family guide. Okay, so back to this case. So how we do this is it's just decimal adding. You can convert everything into decimal or add, or you can just say, not decimal, binary, or you could just add it decimally. So you know that after this instruction, the value in R4 would be what? 1, 2, what?
4. Right.
Yeah, because 1, 2, 3 plus 1, that's already in here, would make this value 1, 2, 3, 4. So that's a pretty simple instruction, pretty intuitive. Our next instruction is and I'm just going to do these alphabetically for now, so I can keep track of which ones I've covered and which ones I haven't. So, and is a little trickier. And let's actually make this interesting. So what and does is it does a bitwise and across all the bits. So in order to figure out what the answer to this would be, you first need to write things down in binary. Or at least it makes it a lot easier if you do. Does everyone know how to convert from hexadecimal to binary? All right. So, if you think back to the truth table of and, what do you get when you and a 1 and a 0? What do you get when you and a 1 and a 1? A 0 and a 1? Yeah. And all of these are going to be with zeros and ones, so we know that all the rest of these are going to be 0. And so then we take this answer and we convert it back into hexadecimal. So and we know that this is the contents of R4 after this instruction completes. Any questions?
So just like 1, 0 is going to be 0?
Yeah, so the truth table of and. You should remember this from your not digital media, modern digital, yeah. So the and truth table, let's say you have so when 0 and 0 are ANDed together, the output is 0. When 0 and 1 are ANDed together, 0. And this one? 1. Ah. So this is what an AND gate does. Does that answer your question?
Yes.
Okay. And then you just do that for all the bits.
And you have to keep that H at the end.
Yeah, so the H means that it's represented in hexadecimal. If you don't have the H, then that means that it's going to be a decimal number. And that is interpreted a little bit differently. You don't necessarily need the H. You can also write hexadecimal numbers with the 0x prefacing it. And there is an interesting little quirk. You cannot actually write hexadecimal numbers if they start with the letter first, like this. You need to start them with a 0 if the first most significant bit is a letter. So otherwise it would be 4 hex digits. But if you start it like with a 1, then that's perfectly okay. So just something to watch out for if your code does something like that you don't expect it to do. That might be one bug. Okay, so the next, let's look at the bit clear and the bit set. Now I'm looking at both of these at the same time because they're pretty much do the exact same thing, only like slightly inverse. But the bit clear is you have some number, usually something that looks actually more like this, where just one bit is selected, and the same for a bit set. And then you probably have it testing some register no, that would be output. Some register like P1 out. Now P1 out is port 1 output register. So that means that this, whatever you write to this register, is an output as a voltage high on the pins, or a voltage low if it's a 0. So what this does is it takes whatever bits are selected in the source of this instruction, and it sets those bits in the same position to either clear or set in this position. So let's say that at the beginning, so up here, before these lines execute, say the value of port 1 out. Now port 1 out is an 8-bit register. Let's say it's some value, and the x's means that we, well, I'll fill those in, not to confuse you. So we have some value in the P1 output register. After this line executes, what this line does is it looks at this bit, so 0th, 1st, 2nd from end, selects this bit and forces it to be a 0. So after this line executes, P1 out is all the same except for that one bit. Because what it does behind the scenes is it's actually not source and destination. So it actually inverts this source and then logically ANDs it with the destination. And bit set is a source logically ORed with the destination. But you can just remember it by saying it will clear this bit or it will set this bit. So this is what happens for bit clear. For bit set, when you have equals some value it will force 1, 2, 3, 4. Bit set will force it to be a 1. And you really can't tell the difference between these, but say if like you had some value that you don't care about in here, well, don't care about at the moment. You'll obviously care about it later in your program. then what the bit set instruction does is makes sure that the bit in this one position is the one right here. Just like how this one makes sure that the bit in a certain position makes it a 0. Does that make sense? Any questions? All right. Should be pretty simple. And you will use bit set and bit clear to either turn on LEDs or like turn off stuff that you want, like to make sure that the output is what you want it onto the pins. Okay, so the next one, bit test, this one is a fun one. It is similar to the compare, meaning that you should really only use it if you have some jump right after. Because what bit test does is it tests the value in the register, and depending on that value, it will say, is it this is 0 or 1, and it will set the Z flag, which is the Z flag is 1 when the previous answer was all zeros, and 0 any other time. Okay. So let's just do an example. So let's have bit test dot B port 1 input. So what this one does is, instead of port 1 out like we had for the last one, now we have a register, port 1 input. And this register reads in the values of what's being applied to your line. So your general input and output pins, you can either set them to be input or set them to be output. By default, they are input, and that's because and that's just so that things, like if you accidentally apply a voltage, it doesn't break anything. So input reads what's being put, action that's being put onto the wires, or potential that's being put onto the wires, voltage. So what this will do is it doesn't care about any bits except for this one. Now, depending on the value of this bit, if this bit is a 0, bit testing it will say, will set Z. But if this bit right here, and port 1 input, is a 1, Z is reset, which means that it's a logic 1. So now why would we want to set the Z? because this is what controls branching, or one way that we can branch. So depending on these two values, we know that, so input, this reads in a value from a button. So say we pressed a button, and input is either here. Let's just say it's active high for simplicity. So we know that when we're not touching the button, it's a 0, but when we're touching the button, it's a 1. Yes?
So basically what it did is switching 0 to 1 and 1 to 0?
No, it's testing the state of 0 and 1. These, bit clear and bit set, would force this to either be so bit clear and bit set are forcing the values. What bit test is doing is it's seeing, it's not writing to this value at all, it's just reading. Actually what it's doing is logical AND, or bitwise AND, but essentially what it does, and what you should use it for, is to read this bit. And this bit is chosen based on this source value right here, the value that you put in your source. So the setup that we have here is we have a button that's either pressed, it's either not pressed or pressed. I guess I can. And it's connected to a wire that feeds into port 1 in. And you can see it in the registers in the microcontroller in this place, in this register, port 1 in. But just because it's read right here, we need to actually program to what to do around it and how to branch. So what bit test does is it gets this value from this random register or like some other place or whatever, this value, and moves it into the Z. Now, the Z flag is what we can jump off of. So there's a class of instructions, the branches, that are used to jump. And these two right here, jump if not equal, or jump if not 0, and jump if equal, and jump if 0, these two things each mean the same thing. This one, you branch to its location when the Z flag contains a 1, and this one, you jump to the location when the Z flag contains a 0. So let's say that right underneath our bit test B, we have a jump if equal to, and I need to make room for myself here. And then we have, and JMP is an unconditional jump. Whenever you reach it, you go to that place. Case B. So, if we don't press our button, and these, case A and case B, are labels, and they will direct to another portion of your code. So, like, you'll have some lines of code here, and then you'll have, like, a loop top label, and then some more lines of code that you wanted the loop, and then at the bottom you'll have, like, a jump if not 0 back to loop top, and continue looping through. Do you all remember that from your assignments? Yeah?
Did you say that the jump if not 0 will jump when the Z flag is set to 1?
Jump if not 0. Let's see. Equals, so if it's equal, so. Oh yeah, you're right. I'm so sorry. There's a lot of things being said and bits being counted, and I'm not actually a computer. Okay, so in this case, say we have our button pressed, and our button pressed writes a 1 to port 1 in. Now with the 1 and port 1 in, oops, we know that Z is reset, and then, thank you, because Z is reset, we know that it's jump if not equal, or jump if not 0. But this jump right here is jump if equal. So where would we jump when our button is pressed? Anyone want to guess? Am I just
Case A.
confusing you all?
Case
Case A. Why would we jump to case A?
Because Z resets.
Because it's checking the Z value.
Because it's checking the Z value. So when we have our button pressed, the Z value is reset, which is set to 0, 0. But when it's 0, we branch if it's not equal, but this instruction is equal. So would we branch to case A here? No, this is actually the opposite case. So we don't branch here because our Z value 0. And this one only jumps when it's 1. But because this is 0, we have to fall through. So we don't jump here, but then we reach this jump statement, JMP, and this is unconditional jump, and this means always jump. So we actually go to case B. Does that make sense? And do you see why you would need a bit test before a jump? Or not that you would need a bit test, but that bit test is only useful if you have a jump right after, or if you want to do something with the 0 flag. Okay. Should I move on to the next instructions? Can I erase this? Yeah?
Why is it not case A again?
Why is it not case A? Okay, so say we want this logic right here. Actually, it's just this. So we want, when our button is pressed, we write out a 1. So this means that our button is logic high, or active high. So that means that when we press our button, it writes out a 1 to this register. Now when we write out a 1 to this register and then run this line of code, it tests the location here. And then depending on this location, it's depending on what is in this value, this sets the Z flag. So after this executes, we have a Z flag. And the Z flag is in the context register, and the context register keeps track of 0 and carry and a whole bunch of other stuff. So here, wait, no.
You'll be 0.
Am I just confusing and talking in circles? Let's see. Right, so if this is 1, so it should output a 1 if we have logic high. So then Z, we go to here and see which one we jump on. And because we know that we jump on 1, JEQ, What? Oh, crap. I'm so sorry. I always get tripped up over this. Hmm. Yeah, I think you're right. It is case A. Okay. So, moving on, an interesting command is the decimally add, and this is useful for adding a binary or a binary encoded decimal BCD number. And you might use it on one of the projects, but it's just something to be aware of. You won't test you on it, but I thought it was a cool command because I've used it before. Next we have the decrement and increment commands. Well, actually, let's roll move into that. Oops. So move sets. Let's make it next here. Say we have an instruction like this. R12 can have anything in it, but at the end of this instruction it has this. Yes?
Just a quick question with move. So say you have like a word in a register and you move a bit to it. What happens exactly?
Okay, yeah, that's a fun case. So say you have this. So at the end of this line, R12 has the content of 4, 5, 6, 7 hexadecimal. If then let's say R12, so this same register into another register, R13, R13 would contain the last bit, or the last byte, and zeros. So it wouldn't copy the whole word, it would just copy the least significant byte, and then the rest would be 0. So even if R13 had something in it instead, like say ABCD, it would now have 6, 7 in it.
That makes sense.
Okay, so we have this value to R12. Increment is a 1 operand instruction. And what it does is it's shorthand for add 1. So if R12 had 4, 5, 6, 7, after the end of this instruction, R12 contain 4, 5, 6, 8. You could do it again, and whatever. And decrement, or the is pretty much the same. Only instead of adding 1, you're subtracting 1. Make sense? Now, the cool part comes when, let's say you had these two instructions. So you load the value FFFF to R12, and what's that? What's that equivalent to? All ones? Yeah. So that's its decimal, but in binary, it's also all ones, right? But our register, or it's actually 16 ones. So 4. That's in binary. All 16 bits are 1. Now what happens when you increment it? When you add 1? Yep. R12 now contains all zeros, and this extra 1 is overflown and goes into the carry bit, or the C flag. Okay. Next are the rotates. Rotate left arithmetically, and rotate right arithmetically. So if you have let's say 4, 4, 4, 4 into R9. And you would rotate on R9. So how you solve for the rotates is you convert this number that's in R9 into binary so that it's easier. And you shift right and pad with the zeros. And the same thing would happen with rotate left, or, oops, that is rotate left. Sorry. Rotate right would result in this, and rotate left would result in shifting all the bits this way. Now, these rotates pad everything with zeros, so even if, like, the most significant bit was 1, it doesn't come around back to the end, or I guess if this is rotate right. This bit doesn't come off the end and go back here. Even if it was 1, it still would be a 0 here. And the only difference between rotate right arithmetically, or the rotate arithmeticallys, and the rotate through carries is that it includes the carry bit in this rotation. So it works the exact same thing. Rotate left through carry and rotate right through carry. Does that make sense?
So if it's RLA and RRA, you rotate it, and if you have a carry bit, you just delete that carry, or it goes straight into the C flag, right?
Through carry, so through the C flag. These, in fact, I think all of them would just pad on with zeros. So it doesn't barrel rotate, at least not in this chip that we're using.
Okay, so RLC carries the C, like the 1, and it goes all the way around.
Yeah. No, it doesn't carry, it rotates through C. So instead of having 16 bits, you would have 17 bits with another C. And so like if this is a 1, and you would rotate right through carry, this one would be added on.
Okay.
So does that move, so like if it's that line, so does that move the last one, that one that you have there, does it move that into carry?
Into carry?
Yeah.
I don't think it does. I think carry only acts as a most significant bit in this case.
Okay.
Any other questions? Okay. Okay, it's almost 7. Okay. So this instruction swap bytes, it just means that if you had, well, in a register, and in that register you had after this instruction you would have, it swaps the most significant and least significant bytes. Swap like this. Okay. And then the last instruction is XOR, which is exclusive OR, which you can use as a toggle. So say you have a value in R5, and R5 is currently FFF0. After this instruction, it toggles it, so it'd be 1.
Can you write the truth table for a song?
XOR? So basically you do the same thing, write R5 out as binary, and then wherever this one is a 1, then you would toggle it. Uh-huh.
your source a hex number, or is it just your
Yeah.
source?
Oh, yeah. Sorry. But hex and decimal, when you're just having one, it's the same thing. You can get away with it, but it's just values larger than 9, you need to remember the H. It's good form to remember the H, I'm sorry. So like you could also have more interesting examples. So let's say that instead of this case, this was all F's. And we had, no, that was a fun one to do. So, you know that the binary for this be all 1 and the binary for this. So if you toggle just these two, you'd be left, or actually let's write it down here. So and this is just taking those last 4 bits, because the other ones are 0 in this case. So you would toggle the bits here. And then, if you were to then XOR again, then you would return back to F. So this XOR is commonly used if you want to flash LEDs so that you don't have to set and clear and set and clear. You can just XOR it and it will turn it from on to off or off to on. Yes?
Your XOR truth table is actually 0, 1, 1, 0.
Sorry, pulling it up from memory. Yes. So that's it for the instructions. There are plenty more instructions in the family guide, but those are usually the ones that you use the most. As far as the actual assembly. So, oh, right. Registers, you have your program counter, your stack pointer, and your context register. And all of these are controlled by your software, so you don't really need to bother with these, except for knowing where they are in IAR to look them up to make sure that things are happening as you expect them to happen. So if in your project you go into IAR and you go into debug mode, there should be a way to view registers and then see all the contents of all the registers. And while you're paused or at a breakpoint, you'll be able to see the values in each of those registers. And that's helpful for debugging. And then of course you have your general registers, R4 through R15, your general use registers. And those are ones that you can use. There's plenty of other registers, like I talked about, port 1 input, and that's a register that reads in data from port 1, and like port 1 out, that's data that you can write out to the outside world. And there's plenty more that you will learn in the next couple tests, or in the next part of the course, and then we'll cover the next few tests. So, on to the memory map, I guess.
Is it not addressing modes?
Or addressing modes? Oh yeah. Okay. So addressing modes are pretty simple, or oops. Have stuff like and this is the case this, you can address this as a literal number. You can also use this for constants. So say you had a constant at the beginning of your program, or you set delay value to equal like 1,000 if you were to use this in a loop. So this, in this case, you would also use this literal number with that constant, because what this says is use it as a literal number, and when your code is compiled, all these constants are replaced with the actual number. So these constants here are just for human readability. So you know, at the top of your program, where you would have or something like that. Let's see. Yeah. So you can make a constant like this, and then when the compiler goes through, it'll find every instance of delay value and replace it with this number. So that's literal. If you noticed, so now we say we want to move R15 into and this is how you address pretty much all registers except for your general purpose ones. You can also use registers as a pointer.
And by general use, registers you mean like R5 through R15?
Yes. Okay. There's also this case where you can use the @ symbol to make R15 a pointer. This actually requires a little bit more explanation. So do you all remember from pointers from C or other classes? Yeah, you get to deal with them in assembly too. So you move the value R14 to R500 or R15, and then you move at R15. So what actually is happening here is R15 contains the value 200 hex. And when you use this at pointer notation, it says, I want to treat the content of R15 as a location in memory. So then, in your memory, it will go to value, or to memory location 200x and store the value in there. Now there's another very similar notation, indexing notation, where instead of using the at sign pointer, you have a number and then parentheses with the register inside. Now, what this is useful for is when you want to not just address 200, but other values too. So you could actually, this number right here is an offset. So if you wanted to get 201 hex, this address in memory, all you'd have to do is change this 1, or this 0, to a 1. And then this value would go into there. And I think that's it for the addressing modes. Anyone have any questions?
What about the $sign? What is that? Or like, does it matter for this test?
$sign, that's used in a very, very specific case. Or I get, so I got this one. Let me just. Keep that one so that you know there's 4 addressing modes that we looked at. Okay, so the $sign is a fairly interesting one. And it's used, let's say when you're defining your memory, so when you're defining your variables, so it's used in this case. So where you're defining your variables, now org200, I'll get to the memory map in a second, but that is the start of your RAM. So this is where you want to store your variables. This line, buffer table DS10, sets aside a space, 10 bytes, for a variable called buffer table. Buffer table size then equals the number of its location minus buffer table. So that means that buffer table size is equal to 10. So you really only use this when you're wanting to keep this so it's dynamic. Because you could set later that buffer table size equals 10 and just remember that this is 10. But if you want to come in later and then set this equal to 12, what this does is it will dynamically remember that. So that if you change this value, and this value is how many bytes you're setting aside for buffer table, it will also change. So it'll reflect how many bytes. Now this is really the only case I've seen it used. But this is a case that is used in some of his projects, in some of Dr. Helm's projects, and on the test.
Do you think you would test that on this test?
Yes. He would ask a question like, what does the DS mean? And in this case, it's define size. Or what is the value of buffer table size? In this case. He won't ask you like the name of this or anything. All right, and that leads into the memory map. Because in order to really understand what this line right here, or 200 does, you need to understand how memory is, or how everything is addressed in the microcontroller. So everything in the MSP 430 has an address. And those addresses are in hexadecimal, of course. And depending on the address, it corresponds to different things. So the addresses from 0 to 1FF correspond with the hardware. You don't need to worry about anything in between these addresses because that's all taken care of for you. And if you try to address into this location, you can seriously mess stuff up by playing around with registers that aren't supposed to be played around with. Or at least not in this direct addressing way. From 200 hex to 3FF hex, you have RAM. And RAM, what do we know about RAM? Does it stick around? No. It's random access memory. That means that as soon as you turn power off, then everything inside of it gets scrambled. So it's only useful for storing variables, a stack, something that you're going to be using as you have power. Random access memory. And then all the way down. This is unused.
The hardware goes from 0 to what? What's that second?
Oh, sorry. 0, 1FF hex. You really just need to remember that RAM starts at 200 and goes to 400. Functionally 300 FF because 400 is like this top right here. And then from C1000 to F1000, F100, and FDF, you have your flash ROM. And this last portion is the interrupt vector table. And you will learn more about the interrupt vector table later.
And what are the squiggles mean?
What squiggles?
400 each.
400H. This just means that it's unused, so that there's nothing there. It's just a wide part of the memory space that is used for absolutely nothing. At least in this microcontroller. There's other microcontrollers that will have different memory maps, but this is only for ours that we're using on our launchpad in this class. So the interesting things here, the numbers that you need to remember are the top of RAM, 200, the bottom of RAM, either 400, or the actual bottom, 3FF, and where the ROM starts. So this flash ROM, this is where your program goes. When you load from your computer to your macro chip, it stores the program, the stuff that you actually type, in here. Well, actually, the compiled stuff that you actually typed in here. And what's interesting about, or what RAM is used for, are the variables and the stack. So the variables start at the top of RAM and build down, and the stack starts at the bottom of the RAM and builds up. And that's so that both variables and a stack can have RAM, but if you have a program that has a lot of variables, then you can be light on the stack and just have a lot of variables. But if you need to use a stack a lot, then it can grow up into the variable space. Okay. So what this line right here means, org 200, means that we're going to start writing stuff in this content in the RAM right here. And so the thing about RAM is that you can't initialize stuff, because as soon as you toggle the power, or cycle the power, it's going to be lost, it's going to be scrambled. But you can set aside portions of RAM to be used for variables. So you could have bar1, define word, so say you want a word-long variable, you would define word, and if you would want a byte-long variable, you would define byte. And these can be used, so like if you have a counter, that you want to have just like some byte-long value, you can define it here. And this is because sometimes the general purpose registers are not enough to do everything in the program. Sometimes you have to save your values to memory so that you can work on other things. Or if you're working with like things and you don't want to remember which register holds what, you can put it in a variable instead. Now it does take longer to access variables than it does to access the registers. These registers are lightning fast right near the other hardware and stuff that actually does the computation. But in our case, really the time delay doesn't matter all that much. At least not how we use it. So this is how you make variables. DW is define word, DB define byte, DS define size. Okay. And then we also use the stack. And let's see. At the beginning of your program, if you use Dr. Helm's code as a starting point, you'll all have this line. You move 400 hex into the stack pointer, and this initializes the stack pointer. The stack pointer is a register that keeps track of the top level in the stack. So that way, when you store values on the stack, it knows where it is. Now, so how a stack works is it starts from the bottom, and then you can push things on top of the stack. So at the beginning of your program, the stack pointer points to the very bottom of the stack. When you use the push command, you store this value on top of the stack. So if the stack pointer is at 400 at the time this line is written, push.w, 1, 2, 3, 4, what it will do is it will save the most significant byte first, then the next, oops, 3, 4. And then it will decrement the stack pointer. So instead of pointing to 400, it'll point to 0FE. So it will decrement by 2. And if you push something else on the top, it will decrement by another 2 and point to this, and so on. One thing to note, that say you just push a byte, it will still decrement by 2, but it will just fill it with zeros, I think. So even if you're pushing a byte onto the stack, it'll still use 2 bytes. It'll still use a full word. Now the stack is automatically used when you use a call function. So when you call a subroutine, so say you have a delay subroutine. So you have some number of lines above delay call delay subroutine, and some number of lines below. The program counter is a thing that keeps track of which line you're on, and when you reach a call, you save the next address. So if this was on line COA2 and the next one had CO or some other address, then it would save this next one onto the stack. And so when you return from a call, because every call you go to a subroutine, and then at the bottom of that subroutine, you have or turn, what it does is it takes the value off the stack, pops it off, and puts it back in the program counter. And that's how it remembers its location when you use the call. And I think that's everything. Does anyone have any questions? Okay. Then you're pretty good to go. I think this covers everything that's on the test. So good luck.